welcome everyone. So let's get some basic things out of the way first. And the first thing is that despite appearances, the name of this course is Lie groups, because that's not anything to do with telling lies. It is the named after Sophus Lie, the Norwegian mathematician. Second thing is that my name is Jason Lotay and I'll be the lecturer for this course, obviously, since I'm here. And the final thing is, please feel free to ask questions about the lecture as we go along, including what is that squiggle on the board? That's a perfectly reasonable question. The handwriting's not going to improve. Okay, so please do ask. Okay, so let's begin. So let's start at the beginning with the introduction. So since you're here, you probably already have this view that groups are great and everywhere. And that's true because they are naturally associated with our idea of symmetries. It's how we encode the idea of symmetries most generally is in the idea of groups, most often anyway. And when we think about symmetries, we often think about geometry, right? With the symmetries of some geometric object. Now, groups are great, but some groups are better than others. And Lie groups are particularly nice because they have their own geometric structure. So not only are they the symmetries of some geometric object, they also have their own inherent geometry. So in the study of Lie groups, what you're connecting is algebra with geometry. But there are also other connections with Lie groups that we will see as the course progresses. For example, there'll be interesting links to topology. Of course, geometry and topology are linked. And then also to analysis. And in fact, that's really where the study of Lie groups came from, was to try to understand the symmetries underlying ordinary differential equations. So what is it that we want to do in this particular course? So let me just give you some highlights of what we are going to do. So the first one is that given any Lie group, we will see that this is quite a complicated object. In particular, it's a nonlinear object because one is doing multiplication. That's obviously a nonlinear operation. But what one can do is taking a distinguished point in a Lie group. Well, in any group, you always have the identity. So that's a distinguished point in any group. So at that point, one can linearize the group. And one ends up with something called a Lie algebra. Okay? So if sort of in your mind, what you might imagine is, say you have a curve, and then you can take a distinguished point on the curve and then take its tangent. Now, of course, if you do that, you've lost a lot of information, right? If I just give you this tangent line, I cannot reconstruct the curve. Right? There are many, many curves with that same tangent line. However, in Lie groups, you can do something very surprising. So for a very large class of Lie groups, it turns out, and we will show, that you can recover the Lie group from the Lie algebra. So in fact, there's a correspondence. So this should really surprise you because, of course, it's clearly not true for the picture I've drawn on the board. And we're going from something very nonlinear, a group, to something much more linear, an algebra. Right? So this is a very surprising fact that we can do this. Now, groups are great, but they're most fun when they act on something. Okay? That's when they're doing something like creating symmetries. And so that's going to lead us to representations. So acting on vector spaces. And we'll do lots of stuff to do with representations. In fact, all of the rest of the course will be about representations. And one of the key things that we'll see is the so-called Peter-Weil theorem. And what this will say is that this will show that there'll be a link between algebra, so we see representations, and analysis. So part of that diagram that I showed over there. We'll actually see that these two things are related in a very key way on a Lie group. The next topic is that in every compact Lie group, we will see that there are distinguished tori, so-called maximal tori, and that will lead us to a fundamental object, which is a finite group associated with the Lie group called the Weil group. And that will help us to understand representations even further. And then finally, I will state but not prove a classification result for Lie groups. And in particular, what's really nice about this classification is, well, in my opinion anyway, is that it's not a regular classification. So normally when you see these classifications, it says it's all the things that you thought of, right? That's normally what classification results look like. That's not this one. So this one will say there are some odd ones out. And in particular, we'll talk about the first odd one out, which is the exceptional Lie group G2. So the eagle-eyed amongst you prove this is one of my favorite things, and I've actually got my G2 mug with me to prove it. Okay. All right, so off we go. Let's actually start doing some maths now and begin with Lie group fundamentals. So just before I get started on this, I have to ask you a question, which is, so raise of hands, is how many of you have done a course on or know about manifolds? Basically everybody. Fantastic. Those of you who have not, just ask me as we go along. Right? I can't do a whole course on manifolds now, right? But they're obviously going to be the sort of building blocks of what we're talking about. So let's just quickly recall just a few things about manifolds. As I said, I'm not going to do a course, but an n-dimensional. So for me, I always drop the adjective in front. So all of my manifolds will be smooth. Okay. So one can define others, but I'm not going to do that. I'm just going to drop the smooth and just assume everything is smooth. So an n-dimensional manifold M locally looks like Rn. N-dimensional Euclidean space. So some examples are given by Rn. Okay, well that's obvious because it locally looks like Rn. And when I mean locally, you can take an open subsets, any open subset of Rn, or of any other manifold M. So if you have a manifold, you take an open subset of it, that's again a manifold of the same dimension. N-dimensional sphere, for example, and n-dimensional torus, which is the product of n spheres. Okay, so these are some basic examples that I hope that you have seen. And this one follows most easily by saying if I have M and N are manifolds, so e.g. also, well, it's part of my examples. If I have two manifolds, then I can build another one by taking their product. And the dimension of the manifold is the sum of the dimensions. The product manifold is the sum of the dimensions. Okay? And what is the point of manifolds? Why? I mean, the definition's a bit weird if you've seen it, but the point is that smooth functions f from M to N between manifolds makes sense. What you have to do is check locally in charts. Charts are where it locally looks like Rn, like some Euclidean space, and we know how to differentiate things in Euclidean space, and so we just check. Okay. Hopefully that stuff is familiar to you. If you have any questions about it, now is the time to ask, because I'm never going to say it again. Are we all right? Good? Very good. All right. So now I can actually tell you what a Lie group is. So this is the definition. A Lie group G, so groups should be called G, right? That makes sense. A Lie group G is a manifold which is also a group. Okay, that makes sense. Okay, so I said it had its own geometric structure. That's the manifold structure. It's a group. That makes sense because it's called a Lie group. But then what I have to say is that the group structure and the manifold structure play nicely with each other, such that multiplication, so that's a map from G cross G to G. Right? I take two matrices and I multiply them, I take two group elements and I multiply them together. And inversion, so I take an element of the group and I invert it, so that's a map from the group to itself, are smooth. So this makes sense because G is a manifold, and therefore G cross G is also a manifold. Right? So it makes sense to do that. Okay. So the key point so I'm not going to ask you to prove in painstaking detail every time that the multiplication and inversion are smooth. If you pick a sensible manifold structure on your group, those things will be smooth. Right? You have to be doing something perverse to make them not. Okay? So it's more going to be, we have something that we know is a group, and we want to prove it's a manifold. If we do that in any sensible way, it will have the property of being a Lie group. Okay? That's what's going to happen. All right. So let's do some examples. So all I want to do for almost the rest of the time, I would imagine, is just go through some examples of Lie groups, because somehow to get, the theory will be abstract at times, and so what we want to do is have a wealth of examples at our disposal so that we can keep coming back to those and get a sense of what's going on, all right, at each step. So let's start with our first example, which is the simplest possible one, which is just n by n real matrices. Okay, so this thing is, of course, the same thing as Rn squared. So this is an n squared dimensional Lie group. Abelian, because what is the rules are addition, right? And that's clearly a smooth map. Yep.
Would it have to be the invertible ones?
No, because my group action is addition.
Okay.
Right? The identity element is 0. Inversion is taking the minus matrix, right? Yeah. So that's why you have to say what are the group. But you've highlighted a key point. Is like I have to say what are the group laws that I'm using, right? Of course, under multiplication, it is not a group, as we know. But this is with addition. Or under addition. Okay. But this one is not very interesting, but somehow this is, one of the simplest ones that we could have. But let's go to obviously a more interesting. This is an atypical example. So let's look at the GLNR, the general linear group. So now this is under multiplication, and this will be sort of our fundamental object, the basic building block. So these are going to be the n by n real matrices such that the determinant is non-zero. And this is just an open subset in MNR, so that means it's a manifold. And then we have to check that the multiplication and inversion are smooth. But we can do that because multiplication, that's just a polynomial map, right, from Rn squared to Rn squared. So that is smooth, because polynomials are smooth. And inversion involves doing some polynomials and dividing by another polynomial, the determinant. So that's, again, smooth, because the thing you divide by is never zero. Okay? So everything is polynomials and ratio of polynomials. So this is a Lie group. Again, n squared dimensional. It's the same dimension as the one before. Okay, but getting any further is going to be tricky because, I need to have some way to build manifolds. But let me just before I say anything more here, we know that if I want to look at the tangent space at the identity of the general linear group, because it's an open subset in MNR, that means its tangent space of the identity is just the vector space that it sits inside. Right? So this is something that we want to keep track of whenever we're thinking about these groups, is its tangent space at the identity. This is because it's going to be related to the Lie algebra of the Lie group. So of course here now this has addition going on. Okay. But to get further, we need to have some way to build manifolds that isn't just Rn and subsets thereof. So let us recall something. I hope this is recall. If you've never seen it before, do tell me. Is the regular value theorem. So let me state this. But hopefully you have seen it before. So what it says is let M and N be manifolds of dimension M and N respectively, and let capital F from M to N be smooth. Okay. Now I let C in N be a regular value of F. So i.e. what I want is that, so this is in addition, so with F inverse C non-empty, i.e. what I want is that if I take my map F and I differentiate it at any point, P, and this is going to be all the points in this level set of F. Okay, so this is some subset of M, right? This thing, the preimage of C. I want to look at all of the points in that subset. That's why I don't want it to be non-empty. Otherwise, I'm not checking anything. Right? So I want it to be non-empty. So I can do this. That if I take the differential, maybe use a capital D here. I'm going to use a small d. It doesn't matter what your notation is. Whatever makes you happy. We're going to take this. This is a map from the tangent space of M at P. And it goes to the tangent space at F of P, which is, of course, C of N. And what I want is that this is surjective. Right, for all the points in F inverse of C. Okay, that's what I want. That's what it means to be a regular value with a non-empty level set. And then the conclusion is, then the preimage C, this level set, is a manifold of dimension. The difference in the dimensions of m and n, so m minus n. And I can also say that the tangent space at any point of F inverse of C, so this should be some vector space of this dimension, but then we know what it must be. It must be the kernel of this differential, because that's what it should be by rank nullity, right? Because if this is surjective, then its kernel has exactly this dimension. So this is the kernel of the differential of f at p for all p in F inverse of C. So I hope that you have seen that before. Have we seen it before? Excellent. Very good. So we're going to put this to good use, because this is great, because it tells us that things are manifolds, and also, even nicer for us, is it tells us what their tangent space is. In particular, it tells us what their tangent space at the identity is, and that's going to be very helpful for us. So let's begin with the simplest possible example that we can do using this technique. And let's do the special linear group. SLNR. So this is the set of n by n real matrices whose determinant is 1. Okay. So of course this is a subset of GLNR, but we're going to restrict ourselves to the determinant 1, guys. All right, so I want to show that this thing is a Lie group and compute its dimension. Right. That's what I want to do. So I'm going to use this regular value theorem just to show you how it works. So, I should say, I wrote this regular value theorem with manifolds. Almost all the time, we're going to pick our manifolds to be Euclidean spaces. Okay, but I've written it in the most general form, but actually we're not going to care most of the time. Right? These are going to be Euclidean spaces most of the time. So in fact, that's what's going to be true in this example. So let F be a map from the n by n real matrices to R be F of A is the determinant of A minus 1. So the determinant, that's a polynomial, so that's a smooth map on the n by n real matrices. So, and I know that F inverse of F is smooth, and the thing that I want to show is a manifold, SLNR, is the preimage of 0. And this is non-empty because we know that the identity is in here. So that's good. So we've checked that. Now what we have to check is what is the differential of this determinant function at points of the special linear group. Right? That's what I want to check. But this is OK, hopefully. We know how to do it. So if A is in the preimage of 0, i.e. SLNR, so the determinant is 1, then the derivative of the determinant of A at a point B is the determinant of A, but that's 1 times the trace of A inverse B. And of course, A inverse exists because A is invertible. That's good. Hopefully this is not a shock to you that I've written this down. Hopefully you've seen this before. Yes? No? If not, this is a good exercise to show that this is true. Okay. That if you differentiate the determinant, you get the trace. Okay, so that's nice. That's a nice map. So this thing is going from MNR to R, right? So this is just some real number. And what I want to prove is that this is surjective, right? So I want to prove that given any real number, And given any a and f inverse of 0, I can find a b so that I get that real number. Okay, so let's write something down. Let lambda be an r, a be an f inverse of 0. And now what I want to do is find something such that when I do trace of a inverse b, I get lambda. So then I'm going to take b to be lambda a over n. And what this will imply is that the trace of a inverse b is going to be the trace of lambda times the identity over n, which is then lambda. Good. So therefore it's surjective. Right. So then, hence, the regular value theorem implies that SLNR is a manifold, but in fact, it's easy to check because we're restricting the multiplication and inversion from GLNR, which we already knew was smooth. The multiplication and inversion are smooth, so is a Lie group. And what's its dimension? Yep.
N squared minus 1.
Yep. Because we're just subtracting the dimensions of m and r, which is n squared, and r, which is 1. So that gives us the answer. So that's great. And we also know what is the tangent space at the identity. And the tangent space, well, the tangent space at any point of SLNR is just the set of n by n real matrices such that the differential is 0, but that's just telling me that the trace of A inverse B is equal to 0. So in particular, we know what the tangent space at the identity is. It's just going to be the trace-free matrices. In particular, the tangent space at the identity of SLNR is just the trace-free n by n matrices. Now, I want to make an observation, which you've probably also seen before, but let's note that if I look at the tangent space at some other point that isn't the identity of SLNR, then I can actually write it in the following way. I can write it as A times B such that B is in the tangent space at the identity. Yeah, we see that? Because if I put this in, I multiply by A inverse, right? So then the A's cancel, and I'll just get that the trace is 0. So in other words, this is just a copy of the tangent space of the identity translated so that it's at A. I've multiplied it. I've multiplied all those things so that now they live at A rather than at the identity. So what this is saying is the following important remark. This is always going to be the case. Okay, this is not a fluke. This is always the case. So if I know the tangent space at the identity, I know the tangent space everywhere. So the tangent space at the identity of a Lie group determines every tangent space. So now it's slightly less surprising, this thing that I was saying, right? This was not the case for just some random curve, But now, I'm saying that if I just know the tangent space at this point, I know the tangent space at all the points. Right? So now it's a slightly more believable that I can recover the group just from the tangent space at one point. It's still not that believable, but it's slightly more believable than it was before. Okay. The other important fact is that this is a general property that we'll use over and over and over, is when I'm studying Lie groups, they're manifolds, so they have charts. But if I know a chart around the identity, then I can get a chart everywhere. So this is another part of the remark, is that given a chart centered at the identity, can get charts everywhere by translation. And this is a trick that we'll use several times in this course, is that I just find the tangent space, or I just do an argument, a local argument near the identity, and then I'll say, but then we've done it everywhere. Okay? So we're going to use that quite a lot. Okay. All right. So far, I've presented some examples of Lie groups, but they've all been non-compact, right? So how about we have some compact ones? So a simple example of a compact Lie group is the unit circle. So S1. So if you like, it's the set of Z in C such that the modulus is 1. Is a Lie group. Is a one-dimensional Lie group. Right. So that's nice and compact. And in fact, what that implies immediately is that Tn, as you'll see, is a Lie group. N-dimensional Lie group. Now, when you see this, if you've got the unit circle, that's the unit sphere in R2, so it's the one-dimensional sphere. And you could generalize that, well, in multiple ways, but there's two obvious ways. There's the way that I did, say it's a one-dimensional torus, and then I say n-dimensional tori are therefore Lie groups. But what about spheres, right? You could say which spheres are Lie groups. And the answer is there's only one other one that's a Lie group, and that's the 3 sphere. So S3, it turns out, is the same thing as SU2, which is going to be a Lie group. We see 3-dimensional Lie group. And then a remark, which of course I will not prove, is that no other positive dimensional spheres, I mean S0 is a Lie group because it's just Z2, but anyway, no other positive dimensional spheres are Lie groups. S7 is almost a Lie group, but it's not, because the product is not associative, and that's one of your rules for groups, is that the product has to be associative. So that's not true for the product on the 7 sphere. Otherwise, it's fine, but I mean, that's a pretty big otherwise. I mean, we really want associativity. Yeah?
I guess it's mostly related. So you have some smooth manifold.
Yep.
When you say that this thing cannot be a Lie group, how does the proof even go? You just try every conceivable group structure?
No. I mean, you have to have some more general theorem that would say, if it were a Lie group, then these other things would have to be true. Right? Yeah. You can't just eyeball it and say there is no possible manifold structure possible with any other group structure. Yeah. There's, it would be hard to prove. That's why I'm definitely not doing it. Right? But it's hard to prove. But they cannot be. Right? I mean, you can cheat by the classification of compact Lie groups, once you know that, then you can just show they're not spheres topologically, but that would be kind of cheating. I mean, but you can do that. So for example, we know all the 5-dimensional Lie groups, so then we can check that none of them is S5, right? And then we'd be done. But this would be one way to do it that doesn't involve very heavy technology, although of course you need to know the classification, which is not easy. And enough topology, of course. Okay, let me do another example now, which is quite similar in some ways. So it's the orthogonal group. So I like this example a lot, and if you've seen it before, I'm sorry about that, but if you haven't, this is very nice. So these are the n by n real matrices such that A transpose A is the identity. So this is this example is a warning example. So let's let f from MNR to MNR be f of A is A transpose A minus the identity. We're basically just copying what we did on this board, right? We're just going to write down the most obvious thing whose zero set is the thing we want. This is smooth because everything is polynomial. So this is again a smooth map between these two objects. So this is smooth. And f inverse of 0 is the orthogonal group, which is non-empty because the identity is in it. Okay, so everything is proceeding as it did before. But now we have to compute the differential. Again, that's proceeding as before. So let's do that. So this is the last worked example I'm going to do. So let's see. So then now we compute the differential of f, a, and b. So this is for any a, actually. We can compute this. We don't need to restrict to things with any determinate condition. B transpose a plus a transpose b. Okay? And then what you would then do is you would go headlong and say, right, I'm going to try and prove this thing is surjective, and you'd run into trouble very, very quickly, because if you look at this matrix, it has a special property, right? This matrix. This is not any old matrix. This matrix is a symmetric matrix. So there's no hope that this thing could ever be surjective, this differential, onto all the matrices, because this thing is symmetric, right? This thing is always symmetric. So I'm going to write sim nr for the symmetric n by n matrices. But if we notice, so we think, oh, well, then all hope is lost, but it's not, because we actually see that our map that we cooked up at the beginning is also a symmetric matrix. So we could have just changed the map and say, well, no, I restrict its codomain to be the symmetric matrices. Right? And this is a vector space, so its tangent space is again the symmetric matrices. So this is now good. Right? This is now something that we can hope to actually prove that this thing is surjective. And so we can, because, but remember, we only need to prove it's surjective when we choose something in the orthogonal matrices. Given anything orthogonal and given anything symmetric, then it's not hard to see, but I'll let you do it, that if you take B to be a half AC, then the differential of f at A of B is equal to C. Therefore, it's surjective. Therefore, the regular value theorem implies that ON is a Lie group. Again, it proves it's a manifold, but as I said previously, it's the multiplication and inversion restricted from GLN, so we already knew those were smooth. So that's okay. So O of n is a Lie group of dimension. Now what's the dimension this time? Someone else, just for variety.
N squared minus n choose 2, maybe?
Yeah, n choose 2, exactly. Half n minus 1, exactly. N choose 2, that's right. Because the symmetric matrices are half n plus 1, and we have to subtract that from n squared. So that's right, precisely. Very good. So it's a Lie group of this dimension. And then we also get that what is the tangent space at the identity of the orthogonal matrices? Well, it's the kernel of this where I put A to be the identity. So it's the B in MNR such that B transpose plus B is equal to 0. So that's the skew in by M matrices. And we can check that, of course, that has the right dimension, n choose 2. So that's great. Now, what we get for free is the following. Note, so then SON, which is the set of A in ON, such that the determinant of A is 1, is a Lie group with same dimension and tangent space at the identity as ON. Well, why is that? That's because it is the connected component of the identity in ON. Because you see, ON, every orthogonal matrix has a determinant plus or minus 1. The determinant map is continuous, so the preimage of 1 must be a connected component. That's the only possibility. Since SON is a connected component of I in ON. So it's an open subset and therefore has the same dimension and tangent space. But if you want to, and I suggest that you do, try and prove it without doing that trick. Just set this up as being, things that are orthogonal in determinant 1, can you prove that it has the right dimension? Okay, great. Any questions before I move on? Okay, great. So now I want to give just 2 more examples, which I will not prove, but will say that they're examples. So these are the final examples I'm going to give right now, is that the unitary group UN and the special unitary group SUN are Lie groups. And I will let you figure out their dimensions and tangent spaces at the identity. So hopefully you know what the unitary group and special unitary group are. If you don't know, just say. Everyone's okay with what they are? Great. Okay. So those are Lie groups. And what we see is that that I've already shown you, in fact, that there are some nice maps we've already defined between Lie groups. We know that if I have 2 groups, then there's a natural class of maps I consider between groups. It's ones that preserve the group operations, so homomorphisms, right? But what's the natural map between Lie groups, or class of maps? So if let GH be Lie groups, a Lie group homomorphism F from G to H is a smooth map and a group homomorphism. Okay, so it's something which preserves, that sort of plays nicely with the manifold structure and plays nicely with the group structure at the same time. And then you can say, when are two Lie groups the same Lie group? So that's when they should be Lie group isomorphic. So a Lie group isomorphism is a diffeomorphism right? So it's a diffeomorphism between Lie groups. So that means it's a smooth map with smooth inverse, smooth bijection with smooth inverse between Lie groups and a group isomorphism. Right. So it has to preserve both the manifold structure and the algebra structure. So we already have some examples of this. The first one is very simple. If I take the determinant from GLNR to R minus 0, so this is a multiplicative group, right? And we know that the group operations here are multiplication, right? Det AB is det A, det B, and stuff like that, right? So this is a Lie group homomorphism. And one more. If I consider the unitary group, and I take it the determinant of any unitary matrix, then I see that that always has to be a unit complex number. So this naturally maps to the unit circle, and this is a Lie group homomorphism for the same reason. I should have said also that, you know, det of A inverse is 1 over det A, right? That's the other thing that we need, and then this means that this will be a Lie group homomorphism. Excellent. So that's some nice maps that we have. I should say, I realized there was one more thing I wanted to say, why I brought this one up. The unitary group and special unitary group, so when you define them, of course, you say that's the complex matrices, complex n by n matrices, such that A bar transpose A is equal to the identity. So you might say that that looks like it's a complex Lie group, but it's not, because this equation is a real equation, right? It has complex conjugates in it. So this is not a complex equation. So this is actually, these are real Lie groups. So that's important. That's why I wanted to bring that up. So unlike SLNC, so if I took my example SLNR and changed it to SLNC, that is a complex Lie group. The determinant, that's a very nice, complex, in fact, holomorphic map, right? Determinant. So that's different, right? So that I can define equations, just because I write down a set of equations on my objects which are smooth, does not mean, of course, that they're holomorphic. I mean, that's sort of an obvious thing to say, but let me just say it again to be clear. Okay, so that's all that I wanted to say today. Next time we're going to talk about this translation business and talk about left and right invariant vector fields. Okay? See you next time.